One of the things that you will realize if you were to use the empirical centigrade scale is that when we make use of different types of thermometers to measure the same temperature, we will end up getting different values. For example, let's say you brought in the mercury in glass thermometer, the resistance thermometer, the thermocouple thermometer to the seaside, and you were to use them all simultaneously to measure the temperature of the ocean. You will realize that they will all give you different values, and the differences are actually not very small. It could be as much as double, right? The temperatures between two thermometers. So why is it so? So in other words, all thermometers measuring temperature on the centigrade scale will never give you the same answer. The reason is because of this. All thermometric properties do not vary linearly with temperature. Now, what does it mean? Remember, one of the important assumptions we made was that the thermometric property X varies linearly or is proportional to temperature. But this is actually, in fact, wrong. And another problem is because they are all not linear relationships. There are also different types of curve. So, for example, if you look at this green color curve and this red color curve, they are all different types of curves. So that's what it means by all thermometric properties vary differently with temperature. So what will happen is they will only agree at the ice point and steam point, which is here and here, because those are the 2 points we use to calibrate the thermometer. So how does this graph show you that they will give you different temperatures? For example, now let's say we are considering the empirical centigrade scale, and we assume that the X varies linearly with temperature, right? So you can see this black straight line here. So let's say we take one of the thermometric properties. Let's say, just for example, we take the length of mercury, which is this green line here. So let's say we place the mercury in glass thermometer in the sea or in the ocean there, and as we place it in the temperature of the ocean, which is supposedly this temperature theta, so what will happen is it will actually show you this length, right? This green color point here, this is the actual length of the thermometer. So however, when we calculate its temperature, we are going to assume that it's part of a straight line. So we're going to use the part of the straight line to calculate the temperature, which means to say its temperature will not be the correct temperature. So similarly, if let's say we place a thermistor thermometer into the same ocean, so at the same temperature here, it will give you this resistance. And if it gives you this resistance, we are going to assume it's part of a straight line. So when we calculate the temperature, we're going to get this temperature. So what you will notice is that these two temperatures are very much different. So therefore, all thermometers measuring temperature on the empirical scale or the empirical centigrade scale will all give you different values. So the problem is, how are we going to solve this problem of inconsistent values of temperature? So what we realize is that since none of the thermometric properties actually vary linearly with temperature, we can no longer depend on them. So we come up with a scale called the absolute thermodynamic scale, and by definition, the absolute thermodynamic scale is a scale that is independent of any thermometric properties. So let me explain to you how it works. Now, we are going to make use of the ideal gas equation. PV is proportional to T. Is because this relationship is supposed to be true, which is supposed to yield a straight line. But the gas that we must use is an ideal gas. So how do we make an ideal gas? Now, what we have is a real gas, but what we need is an ideal gas. So how do we make the real gas behave like an ideal gas? So one of the main difference between a real gas and an ideal gas is that the real gas has intermolecular forces, but ideal gas have no intermolecular forces. So let's talk about, or let's consider why the real gas have intermolecular forces. The atoms of the ideal gas tend to attract each other is because if you consider the structure of an atom, the nucleus of an atom, which is positive, alright, and the electrons which orbit it will tend to attract all the atoms nearby. Why? Because another atom will also have a positive nucleus and electrons orbiting the nucleus. So therefore, what will happen is that the nucleus of one atom will attract the electrons of another atom, and the nucleus of this atom will attract the other electrons of the other atom. So in order to reduce these intermolecular forces to almost zero, so what we need to do is to increase the separation between these two. So the further the separation, the weaker the force, which is why what we need is the ideal gas to be at low pressure and high temperature. Because at low pressure, it means that they're very, very far away. For example, if let's say we have a container and the pressure is very high, and we measure its pressure using a pressure gauge. So what we can do is we can use a vacuum pump and suck out the gas. So when you suck out the gas, as you expel more and more gas from the chamber, wouldn't it mean that there will be fewer and fewer atoms inside here? So the fewer the atoms inside the chamber, it means that there's more space between them. So the forces between them gets weaker. So you keep sucking out the gas until the pressure drops to almost zero. Then you have to stop for a while because you are a little bit concerned that if you continue to suck out any more gas, the pressure will drop to zero. So rather than having an ideal gas, you actually get a vacuum. So then what do you do now? If you want the gas molecules or gas atoms to be even further apart, we increase the temperature. So you heat up this same chamber. So what will happen is, as you increase the temperature, the pressure in the chamber will start to shoot up again. So as it shoots up again, now we at high temperature, we are able to suck out even more gas without being afraid that the pressure drops to zero. So we keep sucking out the gas now until the pressure drops to almost zero again. So now we can be absolutely confident that there are very, very few atoms remaining, because at such a high temperature, it only produces a very low pressure. It means that there are very, very few atoms or molecules remaining. And that's how we create the condition of an ideal gas. So the question is, next, how do we measure the temperature using this ideal gas? So definitely we have to use the constant volume gas thermometer, because it enables us to measure pressure. And the next thing we have to consider is that we have to find two new fixed points, because the fixed points that we use for the centigrade scale, which is ice point and steam points, are not very accurate after all, because these two ice point and steam points, if you realize, will also depend on impurities as well as atmospheric pressure. So the temperature of boiling water may vary a little, temperature of melting ice may vary a little. Now even if you use the body temperature, like in the case of Fahrenheit, it also varies a little between different people. So therefore we need to come up with two new fixed points which are super accurate, that would always be the same no matter where you do it. So the one of the fixed points which they came up with was called the absolute zero. So how did they arrive at this concept of absolute zero? So let's look at this setup here. So you have this gas filled into this flask here, and this flask is then immersed in a water bath to control the temperature of the gas inside here. So what will happen is we're going to measure the pressure of the gas as you slowly reduce the temperature around it from very high to very low temperature. So if we look at this graph here, we're going to see how the pressure of the gas varies with the temperature. So as you reduce the temperature of the gas, the pressure will start to drop. Now of course, if you're using water, then the lowest temperature would be around zero, so you're probably going to get a graph up to somewhere here. So once you reach this point here, then we can extrapolate the line. That means we extend the line ourselves until it cuts the x-axis, which is the temperature axis. So what does it mean? Now at this point here, we will realize that the pressure at this point here is zero, right? The pressure is zero. So this means that at this point, the atoms or molecules can no longer move. Because if you remember the pressure of a gas, the origin of pressure due to gas is because the gas atoms or molecules collide with the walls of the container. So if the pressure is 0, it means that there is no more movement of the atoms. That means its kinetic energy is actually 0. And since the average KE is directly proportional to temperature, so when your KE is 0, this is the lowest ever temperature. So this was called 0, absolute 0. So the guy Kelvin called this 0 and put his name in front, so you get 0 Kelvin. So this was called the Kelvin scale, so he called this point as 0. So however, when Kelvin set this point to be 0 and came up with the Kelvin scale, he didn't want to change the intervals in the Kelvin scale. He wanted to maintain the same intervals in the Kelvin scale as in the centigrade scale. So it means to say that if this originally is 0 degrees centigrade, so therefore this point in Kelvin would be in 273.15 Kelvin. Right, so you notice that the difference between this point, absolute 0, and ice point is 273.15 degrees centigrade. In Kelvin, the difference is also 273.15. It just shifted the 0 from here back to here. So this fixed point here, which is called the absolute 0, is an extremely reliable fixed point, because anywhere in the world, this absolute 0 should be the same. Now, the second fixed point that he chose was called the triple point of water. Now, there exists actually one temperature and pressure such that your ice and water and water vapor can exist in equilibrium, meaning to say the three states of water, solid, liquid, and gas, they exist in complete equilibrium. That means you put them together, then the rate of ice melting to become water is equals to the rate of water freezing to become ice. The rate of water evaporating to become vapor is equals to the rate of vapor condensing to become water. Now this happens only at specifically one temperature, and one temperature only, which is actually 0.01 degrees centigrade. So if we could convert it into Kelvin and maintaining the same interval, it will give you therefore 273.16 Kelvin. Alright, so these are the two fixed points that we are going to use for the absolute thermodynamic scale, because the triple point of water, just like the absolute 0, will be the same anywhere in the world. You cannot have different values. Okay, so therefore we have now established what are the fixed points, what thermometers to use. So let's derive the formula now. So once again, we're going to draw two lines. We're going to assume that the pressure of your ideal gas is directly proportional to your temperature. So here we can use the word directly proportional because the graph would actually start from 0, 0. So pressure versus temperature, the graph will actually start from 0, 0. Alright, so what we're going to do here is to measure temperature, we're going to put the thermometer first into 0 Kelvin, and we measure the pressure. Then we put it in the triple point of water, which is 273.16 Kelvin, and we find the pressure. Alright, let me just rewrite this. Alright, then we put it in the unknown temperature, which is let's say T Kelvin, and we find the pressure. So because it is directly proportional, we can again say that this over this equals to this over this. So therefore, we can rewrite the equation as T minus 0 over 273.16 minus 0 equals to PT minus P0 over PTR minus P0. So since this 0 can be cancelled and the pressure at 0 Kelvin is also 0, we can therefore come up with the formula that the temperature in Kelvin is the pressure at the unknown temperature over the pressure at triple point, the whole thing multiplied by 273.16 Kelvin. Now, one of the problem with the Kelvin scale is that the numbers that you get are often very big. For example, the room temperature could be around 300 Kelvin, all right, or more. So people were not used to the values. So whenever people quoted temperatures in Kelvin, they will end up getting confused. So in order to lessen the confusion, scientists decided to modify the Kelvin scale in order to give you a temperature value that is similar to the centigrade value, which is what everyone was familiar with. So then what happened is, if you remember, the reason why the Kelvin temperature in Kelvin is so big is because the zero starts way earlier, right? So what they did was they're going to shift the zero back to where they found the original zero for the centigrade scale. Meaning to say, what they did was, if you take the temperature in Kelvin and you minus off 273.15, which is how much you shifted the zero in the first place, you're going to get the temperature in degrees Celsius. All right, so when you do this way, you'll notice that your temperature values will be similar to the centigrade values. Therefore, the symbol that we are often very familiar with is also degree C. So, but there is a fundamental difference between degrees Celsius and degrees centigrade. Now, degree centigrade is an empirical scale which is obtained by calibrating your thermometer using the ice point and steam point, whereas Celsius scale is merely a mathematical adjustment of the Kelvin scale. So you could also call it an absolute thermodynamic scale. Now, it is very important for you not to mix up the 273.15 and 273.16. Now, if you are going to use the what do you call it, the constant volume gas thermometer to measure temperature, then you have to use the triple point, which is 273.16. But if you are going to just convert from Celsius to Kelvin or Kelvin to Celsius, then it's sufficient to just use 273.15. Now, some students ask me, but we have always used 273 rather than 273.15. So when do we use 273 and when do we use 273.15? Now, 273.15 is used when you require more decimal places in the question. Okay, but we will see that later as we attempt the past years.
That's all for today's video. If you're interested in more genuine sharing by other geniuses, please subscribe to our channel and don't forget to turn on the notification bell, ding dong. Also, if you're struggling with one or two past year questions and the mark scheme just doesn't seem to help, Genie has got you covered. Feel free to let us know what question it is by filling in the Google form linked in the description below. GenieUs Hub will get genius teachers to fulfill your request for the solution. Genie will see you next time. Bye-bye.